Okay, good morning everyone. Let's continue where we left in the last video. So if you don't know, this is the second part of my video tutorial on how to make a plugin for VCV Rack. So I just had my morning coffee and the caffeine haven't kicked off yet. So as the tutorial progresses, I think I'm gonna get more fluent. Okay, so let's start with the previous tutorial, and in this one what I want to cover, it was initially I'm gonna show you how to make, or actually not how to make them, but how to integrate your custom graphics into the module, and then I'm gonna cover in more details the Vult language. So let's start. I got in touch with Xavier Belmont. So that's, I mean, sorry if I pronounce your name very bad, but French names are always very hard to pronounce, so that's the way I pronounce it. Xavier Belmont, which helped me in the past to make the new look of the Vult modules, and so I asked him if he wanted to create some like ridiculous graphics for the chicken module, and he sent me this, which I think that is really cool. So we're gonna try to make a chicken module look like this, which it has in fact chicken head knobs, which is something that it actually exists. You may have seen it in some guitar amplifiers. And yeah, let me export this again. It was in Rack, plugins, template, resources. Here it is. So it's exported. One thing that it's interesting is that some people commented that they had problems exporting graphics from Affinity Designer compared to exporting them from Inkscape. So and one of the things that I saw, it was that, let me try to show you. So let's go to let me take the compacts, resources, and for example the SVG of Incubus. I'm going to open it with the text editor so we can see it. So what happens is that the renderer used in Rack is not made to be completely compatible, but to be very light and fast. And my guess is that they develop it using as input the SVGs generated by Inkscape, but the ones that Affinity Designer generates are different. So the main difference is that if you have gradients like this, there is a section for gradients, and Affinity Designer puts them in the bottom of the file, and that does the rendering rack doesn't like that, so you have to move these things to the top of the file, like here, and that will work. That will make the trick. So it's just a matter of where the devs are supposed to be placed. If you have problems with any file that you export from Affinity Designer, try that. Try moving the devs to the top, and that may fix the problem. Okay, let's continue. So I exported the graphic, and let's see how it looks. So right now it looks like that, and I want to change the knobs. to the chicken head knobs. What we have to do in that case, we're going to take as reference what is done in Rack to create a widget. So that's the source code of Rack, and let me close all this, and let's try to find where the components are defined. So if we look at the original at our source code, for example, this one first, this is the knob that we're going to change. I'm just going to make a text search, and here it is, component library. So this is the file where all the built-in components are placed, and we are gonna copy this, and we're gonna place it in our template.hpp, which is a file that is included in or that will be included in all the modules that we make. So here we are declaring a new knob. I'm just gonna compile it to see if it works. Okay, so it's complaining because it has the same name. So I'm gonna call this one instead chicken head. Okay, it compiles, but there is one problem here. So this has some specifications. What's the minimum angle, the maximum angle, and then it loads the resources. And actually, I'm gonna remove this part because I just have a simple graphic that I want to place. Let me try to find a simpler one, like this one. This is the trim pot, and my guess is that this is the background part of the knob, and then it has the cap, which the cap should be this part in the center. So as you can see, the cap is not moving while the knob it's moving. So in our case, we don't need the extra part. So I remove it. The other thing is that we need to define where to load the assets, and here we're loading from the global assets of Rack. But in our case, we don't want to do that because our graphics are placed in our component library that belongs to the plugin. So I need to find out how to do that. I guess that the best easiest way will be if you just check. If we just check the source code of one of the plugins that adds custom graphics, like the Befaco. The Befaco has its own graphics, and no, it seems that it doesn't. Maybe they are included in the. Okay, actually, the simplest way will be to check how we load the panel. Yeah, so this is the difference. We're loading an SVG from the assets of our plugin. So I'm gonna copy this line, and this is gonna be our SVG load, like this, and the name of the knob, it's use template. Here it's called chicken knob. I'm just gonna copy the name, chicken knob, and there is no cap. I think it's just like that. Let's try it. plugin is not declared. Maybe it needs to go before. And this is one of the things that I did once, and after that is just copy pasting. So okay, I defined a new SVG knob that loads this resource, and I'm gonna try to replace it. So instead of using these previous knobs, we're gonna use the chicken head knobs. And if everything is fine, it should compile and also load the correct knobs. Okay, it's strange. Did I forget to do something? Oh, maybe the knob takes the dimensions out of the SVG file. Let's try to fix that. Yeah, as you can see, this is not it's not rectangular. So I'm gonna change the size. Instead of being this size in pixels, I'm gonna put 50 pixels by 50 pixels, like that. I'm gonna export it, and this is okay. It's much better. So, but it's not the the location is not correct anymore. So what I'm gonna do is move it a little bit up and a little bit to the left. So instead of being at 87, how many pixels? I'm just gonna use trial and error, because these knobs are not very standard. So it needs to be like a perfectly squared asset in order for me to copy the locations. So I have to make it trial and error. Maybe it was too much. I'm gonna move it a few pixels up. So it's gonna be 87, and it's gonna move to 66, 131, 7, 3. The X coordinate seems fine, but the Y is not correct yet. Not yet. 429. One pixel more, I think. So yeah, that's my recommendation. When making knobs that are not squared, it's much better making it. Yeah, let's do it. So what I'm gonna do is just adding a rectangle. I'm gonna move it to the bottom, and I'm gonna make the rectangle transparent. So now we have a graphic, and yeah, both colors are gonna be transparent. So I can just copy this, gonna group it, copying it, and paste it, and now we have a square. So I can place these ones as centered as possible, and then I can get the coordinate, so which is 86 and 86 in X and 66 in Y. Let's see. Yeah, this is marked a little bit down, but yeah, I'm just gonna move it manually because I was very close already. Okay, it looks fine. It's fine. And there is one thing here is that, as you can see, Rack by default renders a shadow. That's why it looks like that in the background. If I don't want a shadow, if I remember correctly, there was some way of not drawing it. Let me just make a quick search. I actually don't remember what was the name, but okay, so it was added here. Maybe let's try this. Okay, it's a pointer. Okay, now we don't have shadow. And that's it. We have our chicken head knobs. That's perfect. Okay, so that's for the graphics. What I recommend you, if you have custom graphics, just check the component. What was the name? Component. Let me jump back. Component library, where you can see how the different assets are made. For example, the momentary switch. It's when it only has one image, but when you have like switches with different that you want to make, like the toggle switch, it has 3 states. So I guess that this one has 3 positions, and you need to load one image per every position. So just take a look at this file and also to the examples, and I think that you're going to be able of finding one control that matches what you are looking for, and you just check how it's implemented and implement something similar. Okay, now that our graphics are finished, what I wanted to go into it was checking the Vult language. So we're gonna do some more advanced stuff. And in the web page, I have these tutorials, and this is what I'm actually gonna follow. But instead of writing the code directly in the text editor, I'm gonna use the workspace here, which it's nice for making small and simple programs, and it has integrated error reporting. So okay, if you haven't seen this thing, made it quite some time ago. For example, you can. This is the source code of a phase distortion synthesizer, and I'm just gonna play. I think I have a volume. Why is not making any sound? Let's see. Actually, I haven't used it in a while. Okay, this is a simple volume control. We take this synthesizer. And this was my favorite. So it's basically what this thing is doing is that it takes the source code, and I have the full compiler embedded in the web page. So when I press play, it generates the JavaScript code, and then it creates, using the Web Audio API, a custom node which is used to process the sound. and this these controls in the bottom receive events through the control change not on, not off functions that are part of the process. Here we have our main process that takes an input that I think that by default is just a sine wave for testing purposes, and we have to return a single output, which is our rendered audio. So that way we can create a simple synthesizer like this. Let me check. So this one. And if you connect an external keyboard, you can actually play this synthesizer as well. Okay, that's it. Let's start with the tutorial. And yeah, so if you remember last time, I told you that the main reason why I made Vult, it was because I wanted to be more productive when writing DSP code. So usually DSP code is written in C++ or actually in C languages. And the C language, it's a very powerful language. It means C and C++ are very powerful languages, and I have been using them for more than 20 years. But but they have big problems, which is they allow you to do everything, but it makes very easy at the same time making mistakes. So you can shoot yourself in the foot very easily with C++. And yeah, you need to be extra careful because at any point, even if you have been programming it for a long time like me, I mean, you get distracted and you write something that's bad, and that error is gonna haunt you for the next couple of days until you figure it out. Until you figure out that you made a mistake. So in the case of Vult, I wanted to have like more strict checking of the things that I was doing, and also the kind of checkings that I made, it was to avoid making like dumb mistakes. And at the same time, I wanted some language that was as easy to write, let's say, as the simple as the easy languages like JavaScript or Python, but without sacrificing or without introducing the big problems that this language have, which is that you need to run them in order to know if there is an error or not. So Vult it's a kind of a strict language. It's constrained. You cannot do everything with it, but the constraints are imposed. That way I don't make stupid mistakes. And well, and the nice part is that I can just export this code into C++, and since it's C++ code, I can compile it, and it will be as fast as the C++ compiler can make it. Okay, so let's start. I'm gonna create a function that is gonna add a number, and is gonna receive a value, which is x. So the first error that it tells me here is that the variable x cannot be inferred. So Vult has this feature which is called type inference, which is basically that you don't need to specify the type of your variables, but the compiler itself can figure out, based on the things that you write, if the variable it's integer, real, or boolean. So let's say there are two ways of fixing this. One is adding an explicit annotation. So x is an integer, or is a real value, or a boolean value. But we can also set the constraint by writing code. For example, if I say x is equal 1.0, automatically the compiler detects like this must be a real variable, because you are telling me that its value is 1.0. If I say this is true, it infers that it's boolean. And of course, if I set 1 without a dot, it infers that it's an integer. So once we have that constraint in that set, there are other ways in which the types can be inferred. For example, if I say the value y it's equals to x plus 1.0, automatically infers, thanks to this value, it infers that x must be a real and y must be a real as well. Let's make another example. So x and y are real values. And what if I add this 1 plus y? So here the compiler is going to complain. It's going to tell you like, no, you have a type error. You are trying to add one value that is real and one value that is integer, and you need to decide which kind of operation you are doing. So either, so why is inferring that? Because one it's an integer number, and sorry, one is an integer number and y is a real number, so it's not gonna let you do it. You need, if you want to fix this, so what do you want the set to be? You want it to be either an integer or a real. If I want it to be a real, I need to be explicit. This is 1.0, so now it's a real. If I want it to be an integer, I need to convert it first to an integer. So this function converts a real value to integer, adds another integer, and set its integer. So why is this important? So why am I strict with this? So you may, if you have programmed microcontrollers or or a high performance DSP code, it's always one thing that the C++ compiler does is that, let's say that it always tries to upcast your values to the value with the highest precision. Let's say that I want this to be an integer, and in C++, if I just say this, it's gonna compile, it's gonna let you do it, but what's gonna happen is that whatever value this is gonna convert it first to a float or double, then it's gonna perform the operation in double, and then unless I specify the type here, is the value here is gonna be double. If I say I want this to be an integer, then it's gonna be downcast to integer. So there are two conversions, and the conversion that is actually expensive is converting from a real value to an integer. In making that conversion will add overhead to our code, but what we really want is converting the real value to integer, adding as integers, and assigning. So that means if we follow that process, there is only one conversion instead of two conversions, and one operation which is performed with integers instead of being performed with floating point. And you may think that this makes no difference, but since a lot of the code that I generate with Vult is running microcontrollers. I've been like programming Arduino, which is quite slow, or the Teensy boards, which is not as slow but still not very powerful. I want my operations to be very explicit, and still I don't want to write types for everything. So okay, that's basically type inference. So if I keep doing stuff, let's say return c less than 0.0, so complaints. See, it's an integer, so I need to put integer numbers. If I want to upcast and convert to a real value, I can just do this, and the types are fixed. So yeah, that's basically type inference. You need to make the compiler happy with all the types in order to so it will let you continue. Otherwise, it's a big error, and the compiler is not going to let you continue or move forward with your code. Let's see. Okay, yeah. Following this outline that I have. The other thing that I wanted to do, it was making possible returning multiple values. I think that is very annoying. For example, in C++, that if you want to return multiple values, you need to do I don't know, a special type or passing references, which makes the code harder to read. And in other languages like Java, that you need to create a class just to return two values. In Vult is actually quite simple. So I have a function called OP that takes two values and is going to return two values, which is one will be the difference between the two, and the other is going to be the sum of the two. So as you can see, here I'm getting a mistake. I'm getting an error because it's telling me that given the operations that I said, it cannot infer the type. So just by adding one value, it's going to infer the types of everything. So this is a function that takes two real numbers and it returns two real numbers. So how do we use these kind of functions? We can provide two variables to assign. For example, this is going to be the difference and this is going to be the sum. Okay, type error. I'm giving integers and it's expecting real. Okay, that's it. So when calling this function, it's going to return two values, and it's as simple as that. And this is quite convenient when I'm programming synthesizers. For example, I want to make a function that takes a stereo input and I want to get out a stereo output. So I can just make it return two values and bind it. What else do we have? Okay, so yeah, so basically those are the basics of the functions. Then we're gonna move to the section of functions with memory. So I mean, a function, if you have programmed any other language, you may know that a function is like it's its own entity. You have a function, you call it, and good practices in programming are that functions should not hold a state. For example, let's say that I create a function that opens a file, and every time I call that function, I want it to be like a constrained operation. I just want to open the file. If possible, I want to close it, not open the file again, and return me a value, let's say. So what happens if my function opens a file and keeps it open and, let's say, locked? The next time I called the same function in another section of my code, I'm gonna fail to open the file because it's already opened. So we need to add some logic there to protect ourselves on making a mistake. And so the good practice will be to make all your functions stateless. So what is a stateless function is like this. So I have a function that takes 2 arguments and performs some operations and returns a value, and it doesn't hold any value. So I can call this function over and over, and if I give the same input, it's gonna give me the same output every time. So in comparison, let's say that I make a function, I make this function, and then I get time of the day. I mean, this thing doesn't exist, it's just an example. So I do this, I call a function that gives me the time, and I add the time. So this will be a very silly example of a function with a state that every time I call it, it's an impure function. Every time I call it, it's gonna even with the same input, it's gonna give me a different output because the time of the day changes. So in order to make these kind of operations safe, what I implemented in Vult, it was something called, well, it doesn't matter how it's called, but we can see it as that you can define functions that have an implicit context, but which is independent. So I have a very easy example. It's a function that is called counter. I want to make a function that every time I call it, it increments an internal number. So I can say let me remove this line. So what's happening here? You may have noticed before that to declare variables, I use the keyword val, but this one it uses the word mem. So what that means is that it's a context variable. X is gonna become a value that every time the function is called, the value is held. So what's gonna happen if I do x equals counter? So the first time I call this function, the value is initialized to 0. Then it's gonna add 1 and it's gonna store it. That way, the second time that I call the function, the output value is gonna be 2. The third time is gonna be 3, and so on. But here's another characteristic of Vult. Every time you call a function, it creates a context as an independent context. So the way that we can see this is like think that this function, that every function is like a module on rack. It's a tiny module. So if I say this is my function chicken, and if I create another function chicken, these two things are separate. So whatever value I set here is completely separate from this one. Each of these modules has its own internal state. They are completely independent and they cannot communicate to each other. So I cannot move a value here that affects this other module. And this is a good practice because just imagine that you have modules that, depending on the value that you set in one, affect the behavior of the others. So that will be not very obvious, or let's say if there is a mistake or there is some behavior that you don't want, it's going to be hard to figure it out how it works. So the only way, these are the rules, the only way that the modules can communicate is through the inputs and the outputs. Then there should not be any other communication between the two. So that's the same case with the functions. The functions, specifically the ones that have memory, every time you call it, they create a new instance. It's like creating a new module, and the only way that you can communicate with the function is through its input arguments and the output arguments. So what do you think? Let's say I declare the variable x, and I say, and I call it twice. What do you think is going to be the output? So what's going to happen in this case is that this function call creates an instance. So it creates like a rack module that gives you an output, and the second time you call it, it's going to create a new one, and the output values is going to be, in this case, this is going to return a 1, and if I call it again, it's going to return a 1. Why? Because they are complete independent. They are separate modules. What if I want to instead of creating a new module, I want to use the same module? So the syntax to do that is that well, we need to name our instance. This is an anonymous instance. It has a default name, and this other instance, it has a default name. If I want to release it, I need to name it. For example, counter1. What it says here is that this counter that you generated here is called C1, and I have an unnamed. If I want to use again the same counter, I need to specify. So this is my counter1. This is incrementing the number on my counter1, and this is incrementing the number in my counter1 as well. So what happens here is that now the result is going to be a number 2 because we're using the same. So this is very important, and this is very useful in Vult. Let's say that we make a filter, and usually the filters have memory, so they need to keep internal state. And let's say let me go back. If I make them onName, what's gonna happen is that I'm creating 2 filters. It's like I'm creating 2 modules, 2 separate filters. And if I need one more, it's very easy. I don't need to do anything special. I just call the function again, and now I have 3 filters that are completely independent. Yeah, and as I mentioned, this is very useful for writing DSP code, because that's the way I think. So every function is like a small module, and every time I call it, I just want a new one. I don't want the old one. Okay, so like this, the same part is explained here. So one interesting part is that if you check the code that I wrote here for the chicken, I created this function called edge. This function called edge follows that concept. It has an internal memory, and I'm calling it. Actually, I'm calling it only once. Okay, so let's. A better example is the slew. It's the slew limiter that is written here. So this one has an internal state, and here I'm using it independently for the two outputs. So the two outputs may have or have an independent input and an independent output, but I'm not doing anything special. I'm just calling the function and I have a new one. So let's say, I mean, there is one thing in this code that I don't like very much, is that it's not very modular or yeah, it's not modular. So I'm writing a sample and hold twice. Let's say that I want to change this code and I want to create a sample and hold. So a sample and hold is going to receive an input and it's going to receive a clock. And so the first thing that I'm going to do is I need somewhere to store the state. And is what I'm going to do then next is I want to detect the edge of the clock. So the clock signal, I'm going to assume that it's a real value, so I can just copy this part. So what I'm saying is that when the clock signal is larger than 0.2 and there occurs an edge, so it goes from false to true, I want the state to take the value of the input and then I'm going to return the state. So that's it. We have a sample and hold. We have a sample and hold module and I'm going to replace it instead of this. So what I have to do, I will say like sample, it's equals to the sample1 is equal to sh of my input. No, actually this is different. This is different. Okay, so I'm just gonna make something something silly here. This is not the way that I would write this specific code, but it's good for making my case. So we're generating, we have some noise. We're generating it every sample. So what's happening here is that we have this noise, and every time that there is a clock, I get a sample. And if I just repeat these two lines, I'm creating a new instance of this thing, and I can remove this part, so, like this. So yeah, we're using our new sample and hold module, but we are we're wasting some resources because we are generating more random numbers than what we actually need. So one thing that is possible, the way that I will rewrite this code is that I will, since there are two duplicated lines, I can put everything into a single function, which is going to be like a single module, and that is instanced twice, and we can use those two outputs just to simplify the code. So if I want to have exactly the same behavior but simplified, I'm going to call this channel. This is going to be my channel, and it's going to receive a clock. It's going to receive an offset, sorry, a range, and an offset. Actually, it's not going to receive a clock, it's going to receive a trigger. So if there is a trigger, I want to generate a random number. So I'm going to keep memories sample. That way we only generate random numbers, or we call the random generator function only when it's necessary. And then I'm gonna return this part, which is range times the slew rate of the sample. I don't remember what was this. Okay, this was the rate of the slew. I'm gonna put it here, plus the offset. That's it. So what I'm gonna do now is generating my trigger signal, which it was this part. So my trigger, it's equal to the edge of the clock, and this is gonna get simplified. The output one is gonna be the channel that receives the trigger, receives the rate, which is defined by the knob one, receives the range, which is defined by the knob 2, and receives the offset. Yeah, that's it. Let me delete the code of the sample and hold. Let me delete all the code that I don't use. So we use edge, we use the slew rate limiter, we use the channel, and our code it's simplified like this. Let me try to compile to see if it's correctly. No, where did I put it? No, it's here. Okay, so I have some variable declarations that are not used. And that's it. So our model should behave exactly the same, which I think is doing so. The code is a little bit more compact, or at least for me it makes more sense because we are doing twice the same work, so we can collapse it into one. And yeah, that's it. So you can see here that these two codes are exactly the same, but since we're creating separate instances, each of these has its own random generator. Each of them has its own slew rate limiter, but they share only the trigger. So okay, what if, going back to this, I have a counter. Okay, let's say I have this counter, but for some reason, I mean, one of the important parts is that, as I mentioned before, modules should not be able of sending wireless message to each other. And this is a good practice with code. If you're a programmer, you know that global variables are the root of all evil. So, and usually global variables are used to send wireless messages between parts of the code. So there is no way that we can access this value x or modify this value x outside the context of this function. So if I do counter, I cannot modify x only. The only way of modifying it is by calling the counter function, which modifies it the way I want it to be modified. But what if I want to have, let's say, a reset function? If I want a reset function, I need to be able of modifying the internal state. So in order to do that in Vult, you have to create like groups of functions like this. What this means is that these two functions are together. They come in a single package. They come in a single module, and they can be called separate, but every time you call one of the two, it creates a new instance, a new module. So in this function I can do x equals 0. So one thing that you may see here is that I'm not declaring x inside this function, and it doesn't give me an error. Why? Because when I use x here, it's automatically detected that what I meant is this other x. So what happens if instead of using the and, I use fun? So it tells me, no, this is undefined. I don't know what x you are referring to, because these are two separate functions, but with the and, they are together. And we can add more functions. We add more functions to this group. And I don't know, let's whatever name. Then I can do, for example, that x is equal to 1000 or something. So I have three functions. I want to call this like top, counter, reset, and top. So I want to use my three functions in this single piece of code. So I'm going to call, the only way to find out which instance of the counter I'm referring to, it's by naming it. I need to name this C1. So if I do C1, actually I'm not going to assign the value to anything. I'm just going to count. So what this means is that this I'm calling a function or doing anything or doing an operation, and the value that it returns, just discard it. I don't need it. So assign it to nothing. So if I do this, the first time I call it, I'm gonna get, this is gonna return a number 1. This is gonna return a number 2, 3, 4. If I do C1 dot reset, this becomes 0. I mean, it doesn't return any value, but internally it went back to 0. So if I do this again, no, sorry, count. This is gonna give me 1. What if I do instead top? The internal state now it's 1000. And if I do counter again, the internal state is going to be 1001. So we are calling calling functions on a single instance of the code. So this is useful in many cases. For example, I have this in this template example. I have process, that is the main function used to process the signal, and it has all as part of its group, it has these other functions: the node on, which receives whatever I press here, the node off, the control, and the change, the control change and the default. So this allows me to, I'm gonna delete this. This allows me to create, for example, a variable here, volume. I have a variable that is called volume, and every time I receive a control change, I'm gonna assign it. So this is a Midi message. So I'm gonna get the value. I don't care which of these knobs it is. I'm just gonna take whatever value I receive, convert it to real, and then divide it 127, because this is a Midi value and it's gonna be in that range. So if I move a control, this value should go from 0 to 1. And as I mentioned before, input it's a sine wave by default, and I can do input times the volume. So what's going to happen is when I move any of these knobs, it's going to call control change on the global instance or in the main processor instance, which is going to change the volume value. And then when processing the audio, this value is going to be changing and it's going to affect my input. Let's test it. Okay, you can hear how it works. So I mean, I use this in writing the Vult code. I have this structure everywhere. For example, this is my main processing function, and I have extra functions to set the parameters. For example, in the graphic interface, if I change a knob, I usually pass it with one of these functions that is attached to the main process. That way, I don't need in a larger example, in a larger module that has, I don't know, 20 parameters. I don't want to pass all the parameters as an input to the function, because I want just to pass them when they are necessary. So when I change a knob, I have a function like this that changes the value. So actually we can change this one. Oh, so it's exactly what I did here. So the values of the knobs are set by using these functions that belong to my main process, and the only variables that are passed with the function are the ones that can change, that I would like to react to at every sample. So one of the things that someone asked me was making an example of oversampling, and I have this in the page. So this is the typical structure of a biquad filter, and if you have studied some DSP, this is a very convenient structure in which that you can turn into many different filters just by changing the values of these coefficients, B0, B1, B2, A1, A2, and A0, which is usually 1. So, and this is the code for it. I'm gonna copy paste it here. And if we want to make a low pass, we need to calculate the values of these coefficients. And yeah, there are methods for doing it, and there are some like standard stuff. For example, in this file, we get how we should calculate the values for all these kind of filters. So these are simple linear filters, and just by calculating those values in this way, we can create a simple filter. So I'm gonna add, gonna copy this thing as well. So this function low pass uses a biquad, and it provides the values that we have calculated, and it takes the omega, which is the frequency which we want to control the filter. And in this case, well, I recommend you to take a look at this. So the omega, it's the value of the frequency, but in radians, and it's the digital representation of the digital representation of the frequency, if it can be called like that. So what I'm gonna do, I'm gonna take this function. Actually, I'm gonna change the features of the chicken module. So we are not going to do, for this example, the sample and hold. We're going to take we're going to use a low pass, and we're going to filter the input in the modulation 1. So out 1 is going to be the input of the modulation 1. We're going to select one of the values as input. I'm going to take the knob 1. It's going to control my frequency, and the knob 2 is going to control my resonance. Let's see if this compiles. Okay, I'm not assigning any value to out 2. So I'm just going to copy paste, and with the magic of Vult, we have now 2 filters which process 2 signals. Okay, clock doesn't have an annotation, and since it's not used, it cannot be inferred. So I'm going to manually add an annotation type. Boom, we have a filter. But this is, as you may see, this can impose some problems. I'm going to put the values somewhere here. And I'm going to create a VCO. So waves are easier to listen to. Okay, I'm going to put a 1 of 1, and as we can see, it's filtered. I'm going to add a mixer to control the sound. And let's listen to one of the 2. And now let's change the resonance value. And the cutoff. So we have a filter. But there is something special with this structure that I actually know it happens. It actually doesn't get unstable. I thought that it was gonna get unstable, and then we're gonna have some problems. Okay, so it doesn't get unstable. Let's take a look at the power consumption. So it's quite low, since it's a very simple filter. I'm gonna force this example. I'm gonna try to make it unstable. And like that. Oh boy, it's stable. Well, I guess that my example doesn't have sense now. So what I wanted to go to is that sometimes, especially when doing virtual modeling, like the one that I do for the Vult filters and many other of the analog behaviors, what tends to happen is that the system of equations that you obtain may not be stable. And if it's not stable, one way that it can be possibly solved, it's by oversampling your filter, which means that instead of taking one step every sample, every audio sample, let's say if we have a 44K sampling rate, instead of calculating 1 point every time, what we do is calculating twice, like taking shorter steps. that way, in some situations, oversampling can improve the stability. There is a whole theory behind it. Once you get your system, you need to calculate the poles and zeros, and depending on where they lay when you move your values, if they are outside the stability circle, your filter is gonna go unstable and produce an infinite output or something like that. So in some cases, oversampling fixes it. In some cases, no, it doesn't. But what we're gonna do here is I'm gonna create some oversampling of my filters. So what I want to do is basically, instead of calculating 1 point per output, I'm gonna calculate 2 points. And since I'm referring to the same filter, the first thing that I need to do it's module is naming it. So this is my, let's call it my left filter, and I'm gonna perform one step, and then I'm gonna perform another step on the left one. And I'm gonna do the same thing for the second output. This is gonna be my right filter. So if you pay attention to the previous examples, if I don't name the filters, what's gonna happen is that it's gonna create more filters. If they are not named, I'm gonna have 4 filters instead of 2. So this is like the cheapest way of oversampling. Now we have 2x of oversampling. For every sample we calculate twice, but we are doing it the simplest way, which is the first output we're just discarding it, and we're just keeping the second output. There are, if you see the literature in DSP, there are other ways of making this. This is called decimating a signal, or downsampling the signal, and we're actually not upsampling the signal. We're just adding twice the same input. So this is the easiest way of oversampling, and sometimes it doesn't produce very good results. Using another methods for upsampling or downsampling is gonna give you a nicer sound, but for this experiment is good enough. So I'm gonna try to compile. Okay, and now my filter is oversampled with 2x. Well, in this specific case, I cannot hear the difference because this structure is good enough. But let's, I don't know, can we get more resonance? I actually don't know. I need to check the original equations, but I'm just gonna do a silly way. Yeah, we have more resonance. Let's see how much we can add. So this is another silly thing. Instead of calculating the operation 4 times and writing it 4 times, I can just do it once, and I think that is much more readable now. Omega it's equals to this, which is knob 1 times 2. Yeah, much more readable. Okay, so our filter is oversampled, but this is still very light. I don't see any performance hit. So we're gonna do something extreme. We're gonna oversample it so So it's 1, 2, 3, 4, 5, 6, 7, 8 times. 8x of oversampling. 1, 2, 3, 4, 5, 6, 7, 8. 8x. I'm gonna keep the values as they are. Let's see what happens. Yeah, there's some weird stuff happening there. But now it's 8x oversampled. Should we go to 16? I don't even know how many. I'm just gonna copy paste. So what I'm trying to do is increasing the CPU consumption, so my next example makes sense. Okay, one thing that you can hear is that if I go up, nothing is happening. Why? Because I'm oversampling and I need to adjust the cut frequency, so everything is happening here. So this one needs to be divided by whatever oversampling it is, which I don't know right now. Oh, this thing is quite efficient. Well, we have now 9 milliseconds, 9 millisamples of CPU usage. We can exaggerate that even more. Let's see what we get. Okay, yeah, now we have like 14. So the reason that why I wanted to do this is because if you paid attention, this function, the one that calculates the low pass, every sample, we're calculating a cosine, a sine, and we're calculating all the coefficients. And this is not necessary because we need to calculate the coefficients only when there is a change of either the Q or the frequency. So in order to implement that, it's very simple. We can create a function called change that takes a value and creates a memory value, which it will store what's the previous value that we defined. So we can say the return value is going to be if it's going to be true if x is different from the previous. That means if it changed, return true. And we need to remember what was the previous value, like this. So we have a function that to which we input values, and when the values change, we get true. So I'm gonna use this one inside my low pass. So if there is a change in W0 or or a change in Q, I want to recalculate the coefficients. I want to recalculate all this. Otherwise, I shouldn't change them. And once they are calculated, I want to remember them. So A1, A2, A3, no, sorry, A1, A2, B0, B1, and B2. Okay, so this will only trigger if these two values change. I'm actually there may be another error, some bug here, but let's hope it's triggered. That way I can show you another feature. So it compiles, and if you remember the previous CPU consumption, it was around 12, and this one is still around 12. So it's quite strange. Let me check what happened. Well, I actually don't know what happened. Let me remove this line. Okay, it's around that. Okay, I think I know what's happening. So what happens here is that we are checking for a change in the value every sample, but when we add a comparison here, that means that we have comparisons at every point. So what I think is happening is that the C++ compiler is smart enough that when we don't have comparisons, it parallelizes the code. So it sees a lot of operations which are like the same over and over, and it managed to find it determines that it can execute these operations in parallel in a faster way. So that's what I think is happening, because there is no, well, and one requirement to make that work is that that in order to vectorize the operations, is that there should not be comparisons. And when we insert this, we're actually stopping the compiler of parallelizing the code. But I want to break that. Because I mean, this is a special case that happens because this code is very simple. But let's try to break it. How can we break? I need to insert something that the C compiler cannot work around. So let's how can I fix this? How can I break it? I think that is going to be smart enough to see that I'm not using this value, but let's see. No, it cannot break it. Well, my example here is pointless in this case, because it just managed to parallelize and add in the if statement. interferes the parallelization, and then the code that we get is slower. But that's not usually the case. So this code is slower than before. Okay, but this is an illustrative example in which, depending on what you have here, we don't want to calculate everything, every sample. And this is one way that you can do it. Yeah, this is a big bummer, but the C compiler is smart. Let's see if I can make it dumber by adding less optimization. No, it's not 0, 1, it's 0, 1. Okay, this is not gonna work because 01 is set before 03. So if I want to do this, I need to change the optimization flag here, 01. And I can remove it from here. Maybe 01 doesn't, let's try. Okay, so let's try first the case without the comparison. Okay, yeah, so now it's not parallelizing. We get a very high CPU consumption, and hopefully if I put this, our CPU consumption is gonna decrease. Yeah, it decreased. Now it's around 30, and before it was 80 something. So yeah, this is a good example as well. And if you are trying to optimize your code, I mean, there is a rule that says never make a premature optimization. So first write your code, and then measure the performance. And this is a very simple way of measuring it, but you can use a profiler or something like that, and determine what's the things that are actually costing, that cost lots of CPU, and then you can optimize them, because this, as you saw, this was a small change that I thought that it was going to be better, but it actually made the code much worse because it got in the way of the compiler to optimize. So always do optimizations that you can measure. Okay, so that's basically how you can do some kind of oversampling. So the other thing that went wrong in this video was that I was expecting this filter to become unstable, but it doesn't. It's quite stable. And if it gets unstable, then, I mean, if I cannot make it unstable, then we don't need oversampling. Actually, let me remove this. So I remove oversampling. No, actually, I'm gonna keep it. I want to show you another thing, another feature. Now that we can see the impact. So this is the one that calculates everything, every sample. But as you may have seen, okay, it's not a good example. I need to find something else. So what I wanted to show you, it was that Vult automatically calculates tables, which is, I wrote about it here, and I'm not gonna make an example, I'm just gonna show you this. So basically what happens is that sometimes you have a formula that is complicated, like this one. So this one is to calculate the frequency based on the pitch, on the Midi pitch. So if you press a key, you know that every key has a number, and we can convert that number to a specific function, frequency. And calculating this, every time, every sample, it's costly, we know. And also these formulas, for example, this one that has exponential, it can actually cost quite some time. So one feature that Vult has is that you can create a function like this. This one is pitch to rate and implements a simplified version of the conversion formula using exponential. And this is what it returns. But we can annotate. We can use this function that annotates. We can annotate any function, and this feature will create lookup tables automatically. So what we are saying, we want a lookup table. It's usually second order lookup tables of size 127. And the minimum value that I know that this function is going to receive is 0. And the maximum is going to be 127. Why? Because the Midi can only send values for that pitch. So we know that we're not going to get more than that. And I'm asking to generate a table. Instead of calculating every time the exponential, it's going to pre-calculate lots of values and put them in a table, and then performing second order interpolation to make less operations. So a function like this becomes a set of tables. This is a very shorter version of it, which consists on these pre-calculated values, and what instead of calculating an exponential, it just performs additions and multiplications to get the value. So how faster is it? Like in this specific example where this function is used to calculate the pitch of a simple oscillator, of a simple wavetable oscillator, we get some speed up. For example, if we use floating point, this algorithm was using 1.57 seconds to calculate. To calculate, it was, I don't remember exactly how much time I was calculating, but this was the result. And changing that to lookup tables, it gave me a little bit of, it gave me a speed up. And where this makes more impact is it's in fixed point. When I'm using fixed point, this is quite slow, because calculating the exponential in fixed point is it's slow compared to calculating it with floating point. But when we use lookup tables, we get a larger impact. So yeah, just I was writing more stuff regarding the compiler here, and there are some interesting things that I found out. And yeah, I have other comparisons between using mode as in order to grab the phase, and what's the speed up, and what's the performance of different algorithms to generate oscillators. So take a look at this. Just also take a look at the compile, at the tutorials. I have the language reference here, which if you read it once, I think it's gonna give you a very good overview of all the things that you can do with Vult. I mean, the things that you can do and the things that you cannot do as well. Like this thing that I was mentioning, the creation of tables, or even embedding wave files as resources in the code. There are more examples which I created in this repository, so you can see different stuff that I was making, different oscillators, filters. So this is actually, I made this all this code. It was the base for the Vult modules, and then I just evolved them and make them much more complicated. But these are still useful. For example, I don't know, a simple saw wave generator. What else do we have here? Yeah, you can also explore the small synthesizer that I made here, which run completely on the web. And I think I'm gonna cut the video now because I think it's quite long already. Yeah, it's 1 hour and a half. I hope that this has given you a better overview of the features in Vult. And if you have any questions, just write a comment or send a message in the Facebook group, and I will be happy to answer. And that's it. Thank you for watching this. If you made it to this point, you are a hero. Goodbye.